All for coming virtually. It's great to see almost 200 people online. My name is Dr. Chris Anastasiou. I'm the Chief Scientist for the Southwest Florida Water Management District and the seagrass mapping program lead for the district. We've been mapping seagrass for about 30 years. And so what I'm gonna do today is kind of give you sort of a, literally and figuratively 12,000 foot view of our seagrass mapping program. Next slide. And then once we talk a little bit about how we go about mapping seagrass, we'll just delve very briefly into some of the status and trends that we're seeing in Charlotte Harbor and Lemon Bay. And then really I want to spend some time kind of sharing with you some ideas as far as what seagrass mapping are telling us about the overall health of the estuary. Next slide. So I probably don't need to talk too much about why seagrasses are important. I think we all recognize them as both an economic and an ecological importance to the overall health of our estuarine resources. Next slide. In Florida, we have about 2.5 million acres of seagrass. So that translates to about $20 billion annually to the state's economic health. And we also use seagrass as very good indicators of water quality for the most part. And we'll talk a little bit more about that here in a few minutes. But they're also indicators of other stressors as well. So that's important to keep in mind. Next slide. And in Florida, as well as around the world, we've seen a general trend in the downward direction as far as seagrasses and their spatial extent. Worldwide, we've seen about 30% of the world's seagrass habitat lost. In Florida, we've also seen examples of loss just down the road in the Indian River Lagoon. We've seen about an 80% decrease over the past decade. But Southwest Florida has a different story, at least for now. And so we're going to talk a little bit more about that story later. But before we do that, I want to kind of switch gears a little bit and talk about how we actually map seagrass and what it is that we're actually presenting in our map. So next slide. As the title indicated, we have about 30 years worth of mapping experience at the district. My co-author, Dave Tomasco, has really kind of started the seagrass mapping program at the district, and it continues to this day. And we have about 3,800 square miles that we map now, which is the entire coastline of the Southwest Florida Water Management District. It extends from Watershed Bay just to the east of Cedar Key, all the way down to the Charlotte Harbor area. We map seagrass from Tampa Bay south on a 2-year cycle. From about the Piflagoscotty River, right about, if you're familiar with Tampa Bay, right around Anclote Key north, we map that on a 4-year cycle. And so 2018 marks the 30th year that we have seagrass maps. We started in 1988, and in 2018 we flew the Tampa Bay to Charlotte Harbor area. We are in the process right now of doing our 2020 maps, which covers the entire coast that you see on the slide. And there's two main phases, if you will, of our seagrass mapping. There's an acquisition phase, and then there's the mapping phase. So next slide. We'll talk first about the acquisition phase. So imagery acquisition is done via aerial mapping. And we focus primarily on seagrass species, and you can see some of the species that we have here, but we also map other species as well. We also look at attached algae and some other habitats, but it all happens from the air. So when we present our seagrass acreage estimates, we are doing it through aerial photography. So aircraft flies about 12,000 feet, collects 1 foot natural color imagery, and it uses a push broom digital camera like a Leica ASD80 or better. Our acquisition window is between November and February, and that seems like a long operational window, but there's a reason why it goes from November 1st to the end of February. Next slide. And the reason for that is because a lot of conditions have to be just right, and it really is sort of a dance that we have to do in order to make a go, no-go decision for flight. This is just an example of some of the conditions that are required. So if those of you who have who got to see the launch of Dragon on Saturday, not quite as as strict, but we do have very strict conditions. So I can feel for those guys, because many, many mornings we will get on the phone with our flight crews and we'll go over all these conditions. I also want to give a real shout out to the volunteers. Like, I don't know if Judy Ott's online, but Judy was huge, a huge help in Charlotte Harbor. She diligently collected daily Secchi disc or clarity readings at the end of the Bokeelia fishing pier for us, almost throughout the entire period. So that was really helpful. And we have a whole network of folks that go out and collect water clarity data on practically a daily basis for us, because we need to make sure that the water clarity is greater than or equal to 2 meters in each of the locations before we can make that go, no-go decision. So you can see there's a lot that goes into it, but ultimately we do collect that imagery, and it is over the winter, primarily because the atmospheric conditions are clearest then. Next slide. So once we collect the imagery, we go through a process of color balancing, we mosaic the imagery, there's a lot of post-processing that goes on. And then we move into what's called the mapping phase. So the mapping phase, there's really two pieces to that: photo interpretation and field verification. Photo interpretation, as the name implies, means actually looking at the images and mapping the spatial extent of the seagrass that we see, that the photo interpreters see. And they do that using what's called a flux mapping convention. That's the Florida Land Use Coverage Classification System. So it's slightly modified in order to map the distribution of grass. It's important to note that we're not mapping species, we're mapping the signature from the aerial photograph. And that also includes a lot of ground truthing. So the photo interpreters, we have areas that we call areas of concern. We know there are areas that are hard to see. Passes are a good example of that. There's quite a few areas in Charlotte Harbor because of the colored water that makes it a little bit challenging to see. So the photo interpreters will go out and they'll ground truth. Now that's different from the field verification phase. That is a different field component. And what that is it's a way to determine the accuracy of the map. So we go to many points, and this field verification phase has evolved over time. But for 2020, just to give you an idea, across that entire area from Waukesasa Bay to Charlotte Harbor, we are sampling over 1,200 sites. In Charlotte Harbor, about 114, and in Lemon Bay, 42. Next slide, please. And the whole point of that field verification phase is to conduct this, what we call accuracy assessment. So this is a statistical assessment. We are looking at 90% accuracy. So in other words, if we go to 1,000 points, 90% of those points should accurately reflect what the photo interpreters are mapping. If we can achieve 90%, then we accept the final map product. And that's what we're going through right now in the 2020 mapping exercise. All right, next slide. All right, so let me talk a little bit about some of the trends that we've seen. So because we have a nice long time series, we can really start looking at seagrass coverage trends. And again, really, it's important to realize we're talking about the change in coverage, not necessarily species, but just where the seagrass are. So this graph that you see on the slide shows you seagrass acreage from 1999 to 2016. And as most of you who are familiar with our seagrass mapping probably already know, we've seen increasing trends in seagrass coverage really throughout the period of record. In this graph, we're only showing you from 1999. But that's really good news overall. And has, 2016 has been sort of like a record year for seagrass, really across the board, but in places like Tampa Bay, where we've seen a 68% increase in seagrass coverage since 1999 to 2016, that's a really large increase. The other estuaries that you see here, so SB is Sarasota Bay, LB Lemon Bay, CH is Charlotte Harbor, SJS is St. Joseph Sound, and Clearwater Harbor. They're kind of muted in terms of their trend. So if we go to the next slide, we'll see a little bit of a different interpretation of the last figure that you saw. So what we've done here, or actually what Dave did here, I'm not taking credit for this, is he looked at the percent of that 1999 acreage for each of the estuaries. And so this gives you kind of a better idea of the increasing trends that we've seen in seagrass coverage really across all of Southwest Florida. And that's really good news. Now, next slide. But one of the things that we have started to see, and it really became evident from 2016 to 2018, are perhaps a bit of a change in that trend. We've seen really across the entire Southwest Florida area a bit of a leveling off, and in some places a percent decrease in the amount of seagrass mapped in terms of acreage. And that's what this table is showing you. It's basically showing you that, you know, we've seen roughly a 3% or less change in Tampa Bay, Charlotte Harbor. Sarasota Bay saw a slightly larger decrease, and Lemon Bay saw about a 10.5% decrease in seagrass acreage from 2016 to 2018. Now, I want to stop here for a second because it's very tempting to kind of distill all of this down to these numbers. But I want to caution everybody not to put too much stock in just the overall acreage, because it's really important also to look at the spatial distribution of the seagrass and really look more critically at where these changes are occurring. And so that's what we're going to do in the next few slides. I'm just going to kind of take you through Charlotte Harbor and Lemon Bay and hopefully exemplify that point. So let's go to the next slide. And this is Charlotte Harbor. So this is the 2018 seagrass map for Charlotte Harbor. So this kind of gives you a spatial idea of where we're mapping seagrass. And I just put the individual segments in the table on the right. I don't have the segments drawn out on the map, but one of the things I wanted to point out here that's really important is that overall, you know, Charlotte Harbor saw about a 2.8% loss in acreage from 16 to 18. But if you look at it by segment, you can see those numbers are you know, quite variable. The other thing to pay attention to is the acreage change. So if you see like what you should see first in the Mayaca River is a 12.8% loss of seagrass. And that sounds significant, and it is. But if you look at the total acreage, we're really only talking about a difference of about 52 acres. So there's a lot more to these maps than simply looking at the total acreage by estuary. Let's go to the next slide. One of the things that we also do as part of our seagrass mapping program is we look at change analysis. So we take the previous mapping effort and we compare it to the current mapping effort. And so what you see here is the difference between the 2016 and the 2018. So the red areas represent loss, the bright green areas are gains, and then kind of that pukey green color is no change. So by and large, we haven't seen much change, but where you do see the change, that tells you a lot about why these changes may be happening. So you can see along the west wall, it's kind of hard to see on the slide, but there's a thin red line all along that west wall, and that represents the deep edge. So the deep edge essentially retreated shoreward along the west wall. And if you look at the table, Western Charlotte Harbor had about a 9.8% decrease, which translates to just under 200 acres. And by looking at the map, you can kind of infer why that may be. So it's really important to not just focus on the graph that you see on the bottom right, but to really look at where these changes are happening and then to try and come up with explanations for why. Sometimes that's easy, sometimes it's not. Let's look at the next slide, which is Lemon Bay. So Lemon Bay, again, you know, just looking at the distribution of seagrass throughout the bay, 10.5% change. So the question should be then, well, where did that loss happen? Was there one region of Lemon Bay where we saw the majority of that loss? So if we look at the next slide, that's where you can kind of, what I've done on the next slide is kind of zoomed into the northern section of Lemon Bay, because that's where most of the loss happened. And you can see that red area right there is where we saw a trend that went from patchy seagrass to flats, to basically sand. And so again, that kind of allows resource managers to focus on those areas and ask the question, well, what's driving that change? Next slide. So that's what we're gonna kind of delve into here for a little bit, is kind of talk about these drivers. So what is behind these changes? Because this is going to tell us a lot about the overall health of the estuary. It's not enough just to look at the acreage and say, oh, are we increasing or decreasing? It's really important that we look at it from a synoptic scale, but then really go down into a more localized scale and look at it, and then try to ask ourselves, well, what are some of the drivers that are maybe behind some of these trends? So I just listed a few of the more common ones. Obviously, water quality always tops the list in terms of seagrass, but sediment quality can be equally, if not more important, as well as physical disturbances, which we'll talk about in a little bit, and pulsed events, which is also one that we'll talk about here in a little bit. So let's go to the next slide. And I want to spend a couple of minutes really talking about water quality, because water quality seems to be the one that most people think of when they think of seagrass, and perhaps correctly, because it may be one of the few listed on the previous slide that we as humans can actually do something about. So what I've shown you here on this slide is sort of what we call the nitrogen management paradigm, or the water quality paradigm for seagrass. You have a nitrogen load that translates into increase in algae. And in this case, what we're talking about when we talk about algae is phytoplankton. So chlorophyll produced by phytoplankton algae. And on the right side of the slide, you can see there's different flavors of algae. There's epiphytes that are the algae that grow on the leaves. There's benthic algae, which could be anything from drift algae, filamentous algae, the stuff that kind of smothers grass and kind of grows on the bottom. But what we're talking about here, and it's important because it's tied directly to management actions to reduce nitrogen loading, is phytoplankton, chlorophyll in the water column. And why is that important? Well, that's because, as most of you probably know, chlorophyll and phytoplankton algae absorb light. It's what makes the water turn green. So if they're absorbing the light, that's less light that reaches the bottom, and so you don't have as much seagrass. This paradigm works really well in many systems like Tampa Bay. Not so much perhaps in Charlotte Harbor. Let's look at the next slide. Why is that? Well, because Charlotte Harbor, as most of you know, is a color-dominated system. So the water in Charlotte Harbor in many times of the year, especially during the wet season, looks like that. It's very tannic, especially in the upper part of the harbor near the Peace River, Mayaca River. So color dissolved organic matter, or just color, plays a huge role in attenuating light and ultimately regulating where seagrasses can grow, especially along the deep edge. Next slide, please. There's another aspect to color that's important, and that is the ability of color dissolved organic matter to absorb light in the blue wavelength. So that's what this graph is showing you. The brownish curve, the one that sort of has that negative exponential curve, is the absorption function of color dissolved organic matter across the visible spectrum. So 400 to 500 nanometers is basically blue light. It's what is the predominant wavelengths that plants absorb. And so you can see that color really absorbs that blue light. And so it has a very strong, it's a very strong controller of seagrass distribution. Next slide. So going back real quick to the nitrogen management paradigm, this is the paradigm that has worked in Tampa Bay. There's no question that this paradigm is of great use in Tampa Bay, perhaps even Lemon Bay. It will work, where if you reduce the nitrogen loads, you will reduce your chlorophyll concentration, increase clarity, you get more seagrass. I think Tampa Bay is probably the best example of that, where just the point source reduction alone of about 90% back in the late 70s and early 80s had a huge impact. Overall, we've seen a 60% reduction in nitrogen load in Tampa Bay, and we've seen a subsequent growth of seagrass to levels that we haven't seen, well, actually we haven't seen since the 1950s or earlier. Now, next slide. With Charlotte Harbor, we don't think this paradigm really works, and the reason, again, is because color is such a major factor. And so that's something to keep in mind when we talk about nitrogen reduction goals in Charlotte Harbor. And again, when I'm talking about Charlotte Harbor, I'm talking about what we call Charlotte Harbor proper, not Estero Bay, Caloosahatchee, Pine Island Sound, but the harbor itself, greater Charlotte Harbor, if you will. Next slide. And so this is just a graphic showing you what the nutrient loads what nutrient load and average chlorophyll concentration look like, both in the tidal reaches of the Peace River and in that Charlotte Harbor proper area. And really what we see is little to no correlation between chlorophyll and annual nitrogen load. So again, nitrogen loading is a very important thing, but we don't think it necessarily translates into chlorophyll. And that's, again, largely due to the fact that this is a color-dominated system. One thing to keep in mind also is that nitrogen loads are important, and managing nitrogen loads are important. And since 1985, we've seen a very small increase in nitrogen load. The Water Management District had, back in 2000, when we published our swim plan, we adopted a pollutant load reduction goal of hold the line, so hold the line strategy. And it appears that we've done that. Hold the line doesn't mean do nothing, quite the contrary, but it does suggest that we are holding the line in our total nitrogen loads, which is a good thing, even though it perhaps isn't the best measure of, or best predictor of chlorophyll concentration in the water column and ultimately seagrass distribution in the harbor. And Lizanne Garcia is going to talk a little bit more about that later on when she presents the Charlotte Harbor swim plan update. Next slide. So I wanted to, the last few minutes, I just kind of wanted to spend some time on things other than water quality. So those pulsed events that we were talking about, those catastrophic events, if you will, play a huge role in regulating where seagrasses are. And that's something to keep in mind, that water quality is important, but these other events are very important. And you can see on the slide, we talked earlier a little bit about Hurricane Irma and the impact that Irma had. It certainly does play a major role. And there's really kind of, I would say, 2 to 3 ways that hurricanes can play a major role. There's obviously the direct impact of waves, of surge, but then there's also the indirect impact, which again is sort of more linked to that water quality, that flush of water due to rainfall. And I think the third one to keep in mind, not only when we're talking about hurricanes, but when we're talking about all of these potential drivers is, and I'll borrow the term from the insurance industry, pre-existing conditions. So there are cumulative impacts to these seagrass beds, and these pre-existing conditions, if you will, could create more susceptibility in these seagrass meadows. And I think we're seeing that in some of these systems, including Lemon Bay. Next slide. So this is a figure in a paper that was just released. And this is a nice figure because it shows sort of that if you have these pre-existing conditions, if you have these degraded seagrass beds, a hurricane, which hurricanes have been occurring for millennia, so these systems are adapted to that. But if you have a stressed system, then what might happen is you might see a greater impact, not only from a water quality perspective, but hypoxia. We talked about hypoxia as a potential stressor, as well as sediment oxygen demand. So there's a lot of things going on, but ultimately the thing I want to kind of stress is that the trends that we see from our seagrass maps are not just a result necessarily of a single thing like water quality, chlorophyll. It could be many things. It's cumulative impact that can create these sublethal stresses and ultimately destabilize these beds. And hurricane is certainly one of those events that can sort of push these beds over the edge. Next slide. And then, of course, we kind of had a 1-2 punch in 2017, right after the passage of Hurricane Irma. We started to see the onset of red tide, and red tide persisted for quite some time. And so we continue to see this almost cumulative impact on some of these seagrass beds. And so we've seen the result of that since 2017, 2018. So it's important to note those 2018 maps and the plots that I showed you and the maps that I showed you, those were based on photography that was taken between November of 2017 and February of 2018. So really right after Irma, but not quite during the time after the red tide. So we were just seeing the beginning of really the red tide. So the 2020 maps, I think, are going to prove to be a very interesting story. Next slide. And I want to just show you why we think the 2020 maps may be very different because, and this is an example along the east wall of Charlotte Harbor. And I want to thank Mindy Brown and the Aquatic Preserve staff, because those guys are our eyes and ears out there, and they've done some really awesome work. The data that you see on this slide is based on one of their fixed stations. So they have a series of fixed stations that they go out and they map seagrass, or well, they actually go in the water. They're in situ maps of seagrass distribution and water quality. So the data that you see here is from the Aquatic Preserve, from Mindy. And what we've seen, and I think a lot of you have also seen, is this sort of increase in seagrass abundance, or I'm sorry, decrease in seagrass abundance and increase in this macroalgal abundance along the entire east wall. And so we've been monitoring that pretty closely in conjunction with the Aquatic Preserve and others. Betty Stogler as well has been a huge help in this, as well as FWC and Dave Blewett. This is from Lemon Bay, and this is showing you sort of a similar trend in that we're seeing an increase in the frequency of occurrence in algae. The thing that's important to take away from this slide, though, is that in Lemon Bay, you can see this frequency of occurrence of algae increasing as far back as 2013. So that potentially suggests that we may be seeing some of these pre-existing conditions on top of the passage of Hurricane Irma and on top of the red tide. So really important stuff to kind of take. It's a lot of information, but I think our seagrass maps play a major role in that. But as the first bullet here says, you know, seagrass mapping tells us a lot about the health of an estuary, but it doesn't tell us everything. So there's a lot more there. And folks like the Aquatic Preserve, like FWC, like UF-IFAS, very important in terms of being able to provide us with that in-water local information. So with that, I guess it's time for questions.
Yes, Chris, we have about 3 minutes, so if you'd like to get started right away.
Let's see, so November through February is a long window. It is, and is there a correction factor for known seasonal trends in seagrass abundance? Yeah, that it is a long window, and there is some inherent, I would say, potential bias in that, because, and actually it's a good question, because we've talked about moving that window a little bit further to the right, I guess, from instead of November 1st, maybe December 1st, for a couple of reasons. One, November is really starting to look more like September than December in terms of weather. And so you're kind of hitting seagrass at the end of the growing season, going into the more dormant part of the winter. We don't have a quote unquote correction factor, but that is something that we have to take into account when we interpret the maps. Let's see. So there was a question about the hurricanes from 2004, 2005. Yes, there were decreases in seagrass that we saw during that time as well. Whether or not the impact was as great, or as far as the decline is as great, we did see quite a drop, but in some of the segments we saw a significant drop in seagrass, but then they recovered after that. What we're seeing today may, just like in 0405, be temporary. You know, if we have a year or two without hurricanes, without red tide, we might expect to see the seagrass recover in kind, similar to what we saw after the 0405 season. Let's see, regarding the weak relationship of TN load and water column chlorophyll, relationship of TN load and benthic algae epiphytes might be stronger and also bad for seagrass. Absolutely, that's a really good point, and that is something that we are actively looking at and working with our partners on, because, and this is just my opinion, but when you look at water column total nitrogen and you focus only on water column total nitrogen as similar to what the numeric nutrient criteria does, I think you're missing a large part of that story. There is a pathway that goes into benthic algae, and I don't think we've done a good job of looking at that. Our seagrass maps do not map drift algae. We map attached algae, but not drift, because it's drift algae, so it's really hard to quantify, and we don't want to bias the maps by mapping drift algae. But that doesn't mean drift algae is not important. In fact, I think drift algae is a very important component that is often missing And so that's something that we want to definitely take a look at. Am I out of time?
Well, thank you, Chris. Yes, you are, but thank you for that excellent presentation, and we're